Yeah, I saw Cadiz and I was like, of course. I didn't even look at anything else. No. So I have two confessions to make. Well, a couple of confessions, actually. So first of all, I don't really consider myself a functional programmer anymore. I was one before, and I do functional programming, but I'm not just, I don't really would say like I'm a functional programmer. It's a bit of, so I feel a little bit weird standing here. Then the first part of my talk, I'll tell a little bit about my story with functional programming and object-oriented programming. So this is not necessarily super technical, but in the second half of the talk, we'll do live programming. So I'll hope to compensate for that. Also, I've seen a lot of deeply technical talks about stuff like monads and this building interpreters, super cool. My talk is a lot less deep, and hopefully I can make you instead enthusiastic about Swift, because I think Swift has a lot of potential for functional programming. So it's called Wrapping an OAPI. What it really is about, it's about structs and classes in Swift. These are the data types that we have in Swift, and we'll look at them later on during the live programming. So a few days ago, Meyer, who was once a professor in Utrecht, tweeted that he thinks Swift is a much better language for functional programming than Haskell, and it's going to have a lot more influence. And I was a bit shocked by this. Then I remember the stories that people told me about Meyer. He likes to provocate, so he was trying to provoke the Haskell programmers probably. But I think that he has a very good point. If we look at the Swift standard library, it's a lot of functional stuff. There are flat maps in there. Almost all the data types are structs. And as we will see later on, structs are immutable values. They have value semantics, at least. And there's a lot of inspiration from functional programming. So even though you might see a lot of Swift code that's different, keep this in mind. We will get, I think, a lot of new functional programmers into our community coming from Swift. They start with other languages, but they start discovering Swift and discovering what people are doing in Swift, and then coming to functional programming. So a lot of the Cocoa developers I know are now all of a sudden taking courses on Coursera and everywhere, and learning Scala and Haskell and other languages. So it's going to be interesting. Okay, so a little bit about my story. I used to be a functional programmer. Like I would say that I called myself a hardcore functional programmer. I only wanted to do functional programming. Functional programming is the best thing ever, right? It's beautiful. I wrote a lot of Haskell, and I don't have to tell you because you're here at the conference, but it's such a beautiful language, and you can replace Haskell with Scala if you want to. But you know, these concepts, like all the what other languages call generics, we just call polymorphism. It's just a very normal thing for us, and for a lot of languages, this is like this weird thing, and for us, it's like this beautiful normal thing. And I did a lot of type-level programming. I really liked stuff with lenses. So this is about 10 years ago. And I was having a great time. And then after a few years of doing non-stop Haskell, the iPhone came out. And with the iPhone 2, there was also iPhone OS 2. And this was an SDK that was open to third-party developers. And this had this very strange language called ObjectiveC that you would write your apps in. So we downloaded this iPhone SDK a few months after it came out and started making iPhone apps, my friend Ilko and me. And this was really fun. I was writing ObjectiveC, which at the time we would retain our memory ourselves. Like now we have garbage collection, but there we would write retain and release to retain an object to make sure it didn't get released. And if you release an object and the release count got to 0, then it got deallocated. And it was very, very low level compared to Haskell. And it was also painful because there were no such thing as generics in Objective-C. All of a sudden, all of the beautiful functional programming that I knew, I had to throw it out of the window and write Objective-C. And it was very painful. But I really loved the platform. I wanted to make iOS apps. I wanted to do this. In fact, the reason why I got so dragged into it is after we made our first iPhone app, which was a simple game we released ourselves, we made about 150 euros from it, which was also 10 years ago not a lot of money for a lot of work. And we spent all this money on bowling. But what happened after that is everybody started calling us. We want iPhone apps. We want iPhone apps. Build us iPhone apps. And we said, look, well, listen, we just made this one game. We don't really know how to do this. But people still kept on calling and persisting. And at some point, we gave in and started making iPhone apps. And this is sort of how I got dragged into this. Like for about a year, I was making iPhone apps and actually starting to make real money with this, much more than I made with Haskell. I only did one commercial Haskell project. So here I was, a few years in. I was writing Objective-C and writing Cocoa as my day job. However, I had seen the light with Haskell. And this was very, very painful. And actually, I handed in, at the end of my master's, I handed in my thesis, and I was just not feeling well. So I actually got a burnout, and I completely lost interest in programming. And this is, I guess, a danger when you fall in love with technology too much. Then this could happen. There were a lot of other personal factors. But I'd seen the light, and yet I was writing Objective-C. And this was a difficult phase for me. I went through this. It took about a year and a half. Luckily, with freelancing rates, I was able to not work so much. So I was only working very, very little, just enough to pay the rent in Berlin, which is not very expensive either. And at some point, I started having fun again. So what happened is I started a conference on iOS programming because I wanted to go to one, but I didn't want to travel, and there was none in Berlin. So I started a conference, which is always a good idea. If you ever are unsure what to do, just start a conference. And through this conference, I met a lot of people. And at the conference itself, I teamed up with my two friends, Daniel and Florian. And Daniel used to work at Apple, and Florian is just highly intelligent. And with those two guys, we started a magazine called ObjectiveC.io. And this was a major point for me in having fun at programming again. So what we did with this magazine is every month we put out a single issue about something related to iPhone programming. So we would write an issue about graphics, we would write an issue about view controllers, or an issue about audio. And in each issue, we had long articles, and all these articles were edited by a professional copy editor, and we had a really good designer who made a very nice design. And after the first issue came out, people were like shocked, and we were also shocked that people liked it so much. So we had this magazine out there, and after the first issue, we knew that we had to make another one, and we started making issues every month for 2 years. And writing a lot about programming. And this was really, really good for me. Because before, I thought I sort of knew everything there was to know about iPhone programming. I was, of course, completely wrong. And through the writing for this magazine, I learned how much I didn't know. So by writing down articles about a single topic, I learned a lot about all the things I didn't know. And I had to do research, and it was really good. So doing this, all of these steps, like taking the time and doing this, really made programming fun again for me. In fact, I have to admit that I was starting to like object-oriented programming. So it's like, I imagine that most functional programmers come from object-oriented programming, discover functional programming, and really like it. For me, I guess the same thing. I discovered functional programming, really liked it, and then I went back to object-oriented programming, and I'm not completely sure. Maybe it was Stockholm Syndrome. So I was doing object-oriented programming. I'll just show a little bit of some kind of code that we wrote. So this is object-oriented Objective-C. And it might look very horrible to you, and I can agree. So this is like a method called TableView self-erode index path, and it has types there. Because Objective-C is a superset of C, it works with pointers. So these stars are actually pointers. Every object is a pointer. And here we have like a method, a message. So in other words, a method call. So it's the message user at index path, and it gets sent to the object called self. And here's another message, DQ reusable cell with identifier for index path, and it gets sent to TV, table view, and it gets 2 arguments. The reason why I'm saying this and going through this is because this is important to know in the context of Swift. So this is the kind of code I used to write. So no generics, no functions, nothing, just messages. Good. So we're almost getting to the live programming part. Objective-C is all about messages to objects, sending messages to objects. And this idea comes from Smalltalk. So Objective-C was basically sort of a practical copy, but changed, like an extended superset of Smalltalk. The really great thing about Objective-C is that it has awesome interop with C and C++. So because it's a superset of C, you can just call any C function or use any C library without having to do anything, and it works great. You can also write something called Objective-C++, and the people who are not moving to Swift are actually often moving to Objective-C++. It's about as cool or as horrible as you think it is. And this is really awesome about Objective-C. So it's this object-oriented language where you send messages and you can interrupt with C. Then Objective-C doesn't really live alone. It lives in a world called Cocoa. Theoretically, you could use Objective-C separately from Cocoa, but in practice, almost all the Objective-C you write will run on either a Mac or an iPhone or some kind of Apple device. And on the Mac, we have Cocoa as the framework, and on iPhone, we have Cocoa Touch. And Cocoa is an object-oriented framework. And one of the things they love doing in Cocoa is subclassing. I think it's horrible, but they really love it. For example, if you own an iPhone, every screen you see on the iPhone is called a view controller, so every separate screen, sort of. And every view controller, in order to make a view controller, you need to subclass UI view controller. So it's every Cocoa programmer knows how to subclass. We do this every day. For almost everything we want to do, we need to make a subclass of something. And everything is an object. So these are things that are not so nice about Cocoa if you like functional programming. And in Cocoa, there are also some good things. So one of the cool things in Cocoa is that there is a lot of protocols. This is like a Java interface. So it's some kind of abstract definition of an interface, or like a Haskell type class. And Cocoa programmers know how to work with this. And another very cool thing, which sort of surprised me when I learned about it, is that in Cocoa we have mutable and immutable data structures. So you could have, for example, an NS array, which is immutable. And then there's a subclass called NSMutable array, and this one is mutable. And there's also NSData. So this is the one class that we'll work with in a bit. And this is a class for storing bytes, basically. And this is an immutable class. So it has a property length, and it has a property bytes, which is a const void pointer. So a pointer to the first element of the array with bytes. And then there's the NSMutable data class, and this is a subclass of NSData. So that's sort of a strange design, but it allows us to work with NSMutable data and pass it to methods that want NSData. And its endless mutable data has extra stuff for mutating. Of course, I left out a lot of the interface. This is just some kind of stuff. So far, I've been talking to you about my history and about object-oriented programming. This is nice, right, at a functional conference. Because you can feel it coming. Something happened a year and a half ago, and that something is Swift. So a year and a half ago, I was supposed to be at WWDC, the conference where Apple developers go. I didn't go because I couldn't get a ticket. And instead, I went on a holiday with my friend hiking in the Polish mountains. And I was refreshing Twitter to see what Apple would announce. And they announced a new programming language. And I was like, what? And I was hoping it would be something more like Smalltalk. Like I was trying to not dream too big. But it was Swift. And I immediately downloaded the ebook and started reading. And I realized we can do functional programming. And literally, I couldn't sleep. So I tried to move my love for functional programming away and put it somewhere in a box, labeled university. And I tried to just, enjoy object-oriented programming. And then all of a sudden, Apple came and they said, like, here, you have Swift. And my mind was blown, and I was really happy and also a little bit scared. And just to let you know, like, you can definitely not do all of the cool functional stuff that you can do in other languages, but we're getting there. So what happened is Apple announced Swift. I went home back to Berlin and started playing around with Swift. I started getting really excited. And then I convinced Florian to write a book with me on Swift, on functional programming in Swift, because I thought this is the chance. And I just really want to write this. And we decided that we also needed somebody who really knew functional programming, so we asked Wouter Swierstra. I think one of his papers got cited earlier. And with the two of them, we started writing, and it took us a few months. We didn't really know what we were doing, but we started writing this book called Functional Programming in Swift. And we released it in September last year, and a lot of people bought it, and a lot of people had a lot of fun with it. And you have to realize that this Cocoa community, there are people who've done object-oriented programming and Objective-C for 20 years, and now Apple comes with this brand new language, Swift, and they have to relearn it, and they see books like these, like functional programming in Swift, and they get really scared, of course, because a lot of their knowledge is not usable anymore. So we try to sort of sneak functional programming into the system without really saying to people, this is what you have to do, this is the best thing ever, because if I would say that, nobody would believe it. So we try to slowly sneak it in. If you're a functional programmer, you might enjoy it to learn Swift, but probably it's much easier to just read a normal book on Swift, because this is more about functional programming than about Swift language. So we wrote this book, and people enjoy it. It's fun. And what I want to show today is a little bit how we can do functional programming in Swift. And you know how to do functional programming, so what I wanted to do instead is show a little bit of the features of Swift that are really nice for functional programming. So it's demo time. I'll quit my presentation. Let's see. Turn on mirroring. Hopefully. There we go. You can see this. And we're going to start a new project. So this is Xcode. This is the tool we use to write Swift. And it's a very bad IDE, but it's getting less bad. It's actually one of the really cool things about something like Swift and about iPhone programming and Mac programming is that you can write tools that actually run on your phone, or you can write Mac apps. So let's run this program. This is a default command line tool that gets generated. If we run this, it hopefully will print hello world. Let's see. So you can hide this part, and there we have hello world. So far, so good. This was the easy part of the demo. Okay, so what I want to look at is structs and classes. And structs are a way to define data in Swift. And they're immutable values. And this is really cool because I think this is one of the most important things so that we can do functional programming, because they allow us to pass things by value and not by reference. So, you know, stuff like side effects are much harder to do. So, for example, the built-in data type in Swift for arrays is a struct, and it's immutable. So what that means is that we can define something like this. We can define an array of numbers and put 1, 3, 2 in there. And, whoa. So this is how you define an array. And we can print it. So that's the easy part. I'll remove the hello world. And what we can also do, let's see, oh, there it is we can sort them and print that. And this sort function, or method actually, is not changing the array. It's returning a new array. If you're used to functional programming, this is very normal. For Swift programmers or Objective-C programmers, it's not so much normal. However, what Swift also allows you to do is to sort in place. So you can do something like this, sort in place. And this can be very convenient if you're, for example, if you have memory pressure. You can just sort the array in place and modify it locally. But this doesn't work. The Swift compiler gives us an error. And it says that you cannot use a mutating memory on an immutable value. And it even proposes a fix. So if I press enter, it changed this let to var. And the moment it's var, we can sort these numbers. And now we can change the array. So let's run this. So we sort the numbers in place, and then we print the numbers. So this sort in place changed the array. And this is only possible if we define it using var. If I go back to let, it doesn't work. So this is nice, although it's also a bit scary to have to write var, right? Because what does this do? Does it make a reference or something? Let's go a little bit further. I'm going to make it a let again, and we're going to write a function. And it's going to sort and print. Or actually, let's call it sort and print. And it takes some numbers, an array of integer, and what it does, it says numbers sort in place, and then it prints those numbers. Let's rename this one just to make sure we're not actually shadowing something. So here, we have the same problem again. We cannot change numbers. We cannot sort in place because it's defined using let. And we can define it using var. So let's see what happens if we do sort and print numbers. So the cool thing is that, it's called input. The cool thing is that, like I said, Swift arrays have value semantics. So anytime we pass our array to something, for example, to a function, if value semantics means that we pass a copy. So this sort and print, even though inside the numbers are variable, it receives a copy of the original array. So we can even print input to make sure that it really didn't change. So hopefully we'll now get a sorted list printed and then the original input. So here we have 1, 2, 3, the sorted list, and then 1, 3, 2, the original list. So this var is not somehow making a reference out of the array. It makes it locally mutable. And this is very, very useful. And I've noticed that even in my functional code, I'm using var sometimes because it's local, because it allows me to write things in a much shorter way. Another way to have a look at how the behavior of Swift is we can make a copy. So I'll delete this again. So if we make a copy and assign it to input, now we can copy this, sort this copy in place and print it without changing the original input. So just creating a new variable from an existing variable, if that was a struct, it makes a copy. So, oh yeah, sorry, I'll scroll up. you can see that it first printed a copy, which is sorted now, and then it printed the input, which is the original array. So this is how Swift structs work. And let's create our own struct and see if we can replicate that behavior. So I'm going to create a struct person, and it's going to have a name, which is a string, and it's going to have an age, which is an integer. And now I'll create a person for myself. So my name, and I'm 30 years old today. I've been that for a few months, so it's not that it's like it's my birthday. So we can print this. This is how you can create a struct in Swift. So it printed a person with a name and an age. And if we want to change this, we cannot really say something like Chris.name equals John. First of all, it wouldn't really make sense to change a name, but this property is defined using let. So there's no way to do that. What we can do is we can make, for example, the age a variable. So we can write var age as an int. And now we can do something like age++. This almost works. So even though we can now modify the age, we defined our person using let. And this means if you see a struct that's defined using let, there's no way to modify it. So this is very nice and pure. It means it's an immutable value. You can never change it again. Even though this age is a variable. So what we need to do is we need to say var Chris. So now we say Chris is a person that can be modified. It's defined using var. And then we can say age++. So let's run this and print it. Now my age is 31. And you cannot change the name. So the name is always immutable. We defined it using let inside our struct. So it's always going to be immutable. I think this is a very powerful thing. You get very precise control over what's changeable and what's not changeable. And just to be completely sure, we can make sure that we still have value semantics. So if I create a copy, let's say make this one let again, let Chris, and then we create a new copy, Chris2. We can change the age of the copy because it's defined using var. But we cannot change the original value. And hopefully we'll have a copy now. So I'll make this a little bit bigger. You can see that the original value didn't change. So it really made a copy. So what Swift does, it copies every field in a struct if you make a new variable. And one of the other cool things, it only when you change the new value, for example, Chris2, only then the real copy is made. So it's a technique called Copyonwrite, and this makes it very efficient to make a lot of copies because only when they change, the copy is actually made. Cool. So I'll remove this copying again, and let's change this to a class. So, like I said, Swift is sort of like a replacement for ObjectiveC. Don't tell the ObjectiveC programmers, but it's going to be like that soon, I think. And therefore, it's very important to interoperate with ObjectiveC and with Coco. So we need to be able to make classes and not just structs. And this is how we can make a class. We'll also need an initializer, so I'll quickly write one. So this is how you can make an initializer. And you just say self-name equals name and self-age equals age. So this is how you can make a person class. So it's almost the same as a struct. And if we run this, we can print the age and the name. And let's see what happens. So it just is almost the same. However, if we make a copy now, and we say Chris2.age++, what happens if we log Chris2 as well? So now we log Chris and Chris2. they both have an age of 31 all of a sudden. So what's happening here is how Swift objects work. They're reference types. So this doesn't make a copy of the object, it makes a copy of the pointer. So now they both are separate references, but they refer to the same object. And it's very important to notice when you're dealing with Swift and when you're dealing with object-oriented APIs in Swift. So this is how that works. So I want to change it back to a struct and show one more cool thing with mutation, and then we're going to actually do what I promised and wrap an object-oriented API. So what we can do is add a function to mutate a struct. So for example, we could do something like this, extension person, and add a function to celebrate somebody's birthday. Celebrate birthday. And what this will do is it will increase the age, and then it will print, let's see if we have a nice emoji for that. It will print happy birthday and a new age. So as you may have expected, Swift doesn't allow us to just modify the age. This celebrate birthday, this would be a side effect. And if you would define a person using let, and you say age, and you call celebrate birthday, does it change the age? That would be horrible, right? It's very unsafe. So Swift tells us we have to mark this method as mutating. And by marking it as mutating, it can only be called on vars. So let's go back and say something like Chris.celebrate birthday. If we run this, we get a build failed. And this is really nice. We don't want to be able to call this method because we define this Chris using let. And only when we define it using var, the build succeeds. So that's how you can work with mutating methods in Swift and make sure that your data is immutable and only mutable when you want it to. And as you saw, if we remove this mutating, the code will not even compile. So the compiler will not allow us to do this. So there's some really strong guarantees there enforced by the compiler. So that's how Swift structs work. Let's take a look at NSData, which is a class, and then we're going to wrap it so that it has the same kind of behavior. So I'll delete this. We're going to make some data. So what you can do is, for example, if you have a string, you can say data using encoding. Example data. And this encodes it as UTF-8 bytes. UTF-8 string encoding. This example data, if you look at it, it's an optional NSData. So we know that it will always work. This will always be non-nil, so I'll just force unwrap the optional. And we can print this. There we have our data. This is hello world in bytes. So what we can do is something like this. So we can create some mutable data. Let's call it data. And it's an NS mutable data. And it starts empty. And then what we can do is we can say data that append, example data, and we can log, for example, this new data. So print data. So this works. If we make a copy, let's do that before the appending. If we make a copy, what we really would like is the same kind of behavior we had with structs. So now we create a copy, which is also NS mutable data. And then if we print both, now, of course, because it's classes, they share the same reference. So they're the same object. So that's not really cool. This doesn't make a copy. It only makes a copy of the reference. And how can we get this behavior? the problem gets even worse before we start building this struct. So I'll show you one more example. If we create a function, let's say process data, and it processes some NS data. For what we can do in Swift, for example, is check, like, let's make sure that the data is not empty. And here we start processing. We can call this process with mutable data. This is because NS mutable data is a subclass of NS data. So it sort of fits, the type fits. However, inside this function, we have no idea that this data is actually mutable. So if somebody on another thread starts mutating this data, this guards, even though it might be true in the beginning of the function, it might not be true later on. So it's really, really hard. And this is the problem of mutable data and multi-threaded programming. In Swift and in Objective-C, there are no guarantees. So this is a problem. What we are taught to do as Cocoa programmers is always to do something like this. So, so we can say let copy equals data.mutable copy, or actually, in this case, data.copy, which because of an Objective-C implementation detail, we also need to cast. And then we only work on the copy. And now we know that we have our own unique copy of the data and nobody can change it, and we're fine. In Objective-C, there's also NS mutable array, which is the default way of creating arrays. And there are a lot of bugs that exist because of this, because an NS mutable array might be passed as a normal array and mutated in the meantime on a different thread, and code will completely crash. So this is problematic. Let's fix it. I'll delete this again. What we can do is we can create our own struct. And inside this struct, we store some mutable data. Mutable data. We can start maybe with empty data. Whoa. And I made a typo. Cool. So inside the struct, we store mutable data. And now we can create an initializer that takes some data, which is an NS data, and it appends it, because you start with empty data and then you just append it. Append data, some data. We can even provide a default value, empty data. So now we can create values of this data struct. So for example, like this. Now we have empty data and it's a struct. We can run this. Not much will happen. It's not very interesting yet. We can also put something in there. Some data. What was it called? Sample data, example data. So we can put something in there, and that works. However, let's make this a little bit more interesting and actually implement the copy behavior. So first, I want to add one more property, and that's the bytes property, which returns us the bytes in the data. And this is how we can do that. We can define a computed property with var and a block. And what we can do is use on NS mutable data, get bytes. And here is, this is the wrong one, get bytes. Here is a nice example of how we can work with a C API. So this unsafe mutable pointer void is really a C void star. And what we can do is just create some kind of array result, which is an uint8 array, and use that as our unsafe mutable pointer. Hopefully we get autocompletion. No. Let's see. So we want an empty array filled with zeros. So let's see. I think this is the repeated value. So we want an empty array filled with zeros of the right length. And we can pass it in to our data get bytes, just like this, and also use the data.length. And this is a very unsafe operation, which is on the C level, but we can wrap it, and then we return the result, and our code compiles. And what we did here is we took a C kind of almost very low level function call, and we made it very safe. Now the bytes is just a uint array, so we can take complicated APIs and make them very simple in Swift. So we can print data.bytes. So far, so good. Let's write append. So if we want to append something, we can just take the other data and append it to our existing data. So we can just say data.append other data. We'll mark it as mutating. That way we can only call the append on a var and not on a normal let-defined data. So if we, for example, want to try data.append example data so that it's in there twice, we get an error because we marked append as mutating. And we can change data to a var, and now it works. So let's see if this compiles and runs, and if the bytes are in there twice. So it's a lot longer, the array. Let's make a copy. That's the other part, right? We have now this append hid behind mutating. That's good. If we make a copy, does this work as well? So now I expect that the copy has just the example data in there once, and then the data has the example data in there twice. Let's see, there's a long array, and there's another long array. Oops, there's some kind of mistake. So what I expected is that they would have a different number of bytes because we made a copy. We only appended to one of them. The problem is that we have to think again about how structs work. So if we make a copy of a struct, every field is copied. And in this case, there's only one field, the data, and it's actually copied. But it's not the object that's copied, it's the pointer to the object that's copied. And that's why, even though we have a separate struct, they share the same pointer, and they share the same immutable data object. So this is something we need to fix. Actually, what we need to do here is we need to make a copy of the data before we append to it. So what we can do is something like this. Data.mutable copy. Then we need to do the force cast again. And only append after making this copy. Self.data equals. So now, let's see. We need to change the property to var. It's private, so it's fine. And now we can see that here we have a short array with only the hello world bytes, and here we have the array with hello world in there twice. So functionally, our solution is correct. Let's see about efficiency. So if we create a for loop, let's append something maybe 10 times. What happens? Well, if we think about it, of course, now a copy is made every single time that we append data, and this is highly inefficient. The first time, like here in this line, we really want a copy to be made, but inside this for loop, we're just changing the same value over and over again, so there's no need for us to keep making this copy, but it's still happening. If we add a print line statement, making a copy, just to debug, then we'll see that this is printed 10 times. And we really only wanted it to print once, because we only have one real copy. So what can we do about this? Let's see how we're doing on time. I think we can squeeze it in. There's special support in Swift for these kind of problems, because like I said, everything in Swift is a struct, and in the Swift standard library. However, in the Swift designers also care a lot about performance, and it can be very useful to have low-level implementations behind those structs. So we want value types, but we want them super efficiently, like, for example, using NS-mutable data or using raw C pointers. What we can do is use a function called isUniquelyReferenced non-ObjectiveC. It's a long name. So what this does, it checks if an object is uniquely referenced. For example, the mutable data at this point, after line 25, it is uniquely referenced because there's only one copy of this NS-mutable data. Here, at line 27, it's shared with other. It's not a uniquely referenced anymore, but once we start appending to this same thing over and over again, it's uniquely referenced. There are two copies of the data, and both are unique. So we can use this function, except that it says non-ObjectiveC. And NS-mutable data, and this is an implementation detail, and it pains me a bit that I have to show it, but NS-mutable data is an ObjectiveC object. We cannot use it with an ObjectiveC object. So we have to create some kind of wrapper, some kind of Swift wrapper around ObjectiveC objects. So let's do that very quickly. We're just going to create a box that takes any kind of A, and it can unbox, which returns the A. So it just stores the A sort of as a variable, and it needs an initializer of type A, which just stores the value. And this is a way so that we can put anything inside this box, and it's a Swift class. We can put ObjectiveC objects in there, we can put structs in there, or just Swift objects. Now we can change this private variable to a box of NS-mutable data. And we also need to change it here. This, we now need to unbox the data here and also here and here. We can make this nicer, but we lack the time for that. And here we can now check if this object is uniquely referenced. So let's do that. So if it's unique, self.data, if it's unique, it means that we do not need to make a copy. So we can just append to it other data. If it is not unique, then we need to make a copy. You can see the duplication in this code. And then you can see the duplication, and you can totally refactor that to be nicer. So here we make the copy only if it's not unique. And then here we say unbox. So let's see what happens. So we have a short array, so this means that it's not the same. So there's still semantically two different values, but the making a copy is not printed anymore. Making a copy, and hopefully this will be printed only once. So it's only up there once. And you might think that this is a bit of a strange and very complicated technique, but I've used this successfully also, for example, with a C library for parsing Markdown. I did all the parsing and then the C nodes in just low-level C, and then I made a nice Swift wrapper around it to modify all the elements and to change everything in a nice Swifty way with structs and enums. And at the end, I went back to C again. And it allows us to create data structures that are not so beautiful under the hood, but highly efficient, yet they are very native to Swift, and they have value semantics. Right. So let's go back to the slides. I have one more slide. And that's the thank you slide. I hope you had a lot of fun, and I'm very happy to take any questions if we have time. Thanks.